as you know, breast cancer is a major, you can actually call it a pandemic, although it's not infectious. It's a pandemic, it happens across the world. And then the primary concern for breast cancer nowadays is what we call a triple negative breast cancer. Now, all the other types of breast cancer, like hormone positive and all the other pathologies that you come across, are treatable. Even at the stage 4, they're completely treatable. Whereas triple negative remains a major, major unmet need in the field. So just to give you a small introduction to laser pointer. All right, is my pointer visible?
Yes, it's visible, Sourav.
Okay, thank you. All right, so if you look at the general progression of cancer, this is common to all forms of cancer. So this is common in brain, breast, lung, epithelial, colon, whatever you can think of. So this is a normal epithelial tissue. That's a normal tissue that we have. And then when there's an early adenoma, so an adenoma doesn't necessarily mean it's cancer, it's just a mass of cells. The cells, they multiply, a little bit abnormal, they multiply and form a polyp. And if you know, in India, you often go for colonoscopy when a person is above 50. And in the colonoscopy, they try to look for these polyps because these polyps are almost predisposed to form a cancer later on in life. That's why identifying these polyps is important and as early as possible. So from the early adenoma, we get something called an intermediate adenoma, where there are two masses of cells which are proliferating at a faster rate than normal. And finally, we have a late adenoma. And late adenoma is a very solid, large tumor. Although need not be cancerous, but it could be benign, but it's still a tumor. It's classified as a neoplasia or a tumor. And it's almost definitely predisposed to form a cancer. And finally, in the end, we have what is a carcinoma. All of you are probably familiar with this term. Carcinoma is a full-blown cancer, a tumor. It's anywhere between 2 millimeters going up to 10 millimeters or higher. And these are completely cancerous, and they would cause fatality down the road. And finally, the final stage of it is metastasis. If you're not aware of this term, metastasis basically means, when the physician says that, oh, your cancer has spread. So that spread is actually called metastasis in the biological terms. So metastasis is basically where the cancer from, say, if the primary cancer is in colon or in lung, it's actually invaded through the tissue, moved into the blood, and now spread across the system. And it could be now be present in the brain, it could now be present in the gut, it could be anywhere. And that is the last stage of cancer. And it's, at this point of time, a metastatic tumor is almost incurable. It's just a matter of time, and the patient is in palliative care. So now, Dr. Ganguly, if you could just let me know. I'm going to ask a few people to raise their hands. And would that be visible to you?
Definitely, definitely.
Okay, I'm going to ask the students to raise their hands, okay? Not the students, everyone to raise their hands. Just, I want to see what you think. So, do you think cancer is an ancient disease or it's a modern disease? How many of you say it's an ancient disease? And how many of you say it's a modern disease? Right. What's the ratio roughly? Dr. Ganguly, can you just tell me what the ratio is roughly?
So most of them have raised their hands for it's an ancient disease.
Yes, that's the first time that has happened. Everywhere else, I've asked them to raise their hands. They have said it's a modern disease. Right. So let me tell you how ancient this disease is. So the first record of human cancer is found in 3000 BC Egyptian papyrus in hieroglyphic script, wherein the physician was actually noting down all the human diseases on this papyrus. And then the person actually explained the disease, wherein there was a lump in the breast of a female patient. And then in the treatment section, it said no treatment available. And that is the first record of human cancer, and that's 3000 BC Egyptian papyrus. The first evidence of cancer ever and this is a surprise probably for most of you, the first evidence of cancer in any organism, the oldest evidence of cancer is an osteosarcoma in a dinosaur that was 77 million years old fossil. It was a triceratops fossil where the bone clearly had a fossilized tumor on it and it was invading into the bone and going into the bone marrow. A classical osteosarcoma found in dinosaurs 77 million years ago. And finally, who coined the term cancer? This is probably many of you may know this. This was actually Hippocrates in 400 BC, where he described a female patient to have a lump on the breast, and this looked like a crab, and that is why he called it carcinos, the same as the zodiac sign Cancer. He called it carcinos, and then eventually it became cancer. So you see, this is an ancient disease, a really, really old one. And the only reason we see more incidents nowadays is because we have better detection system and also the environmental factors that play in the development of cancer. So let me give you a short background of how the first causation of cancer was discovered. Now, this is an interesting story, and this is actually a story of a chicken virus. That is sounds surprising, I know. It's a chicken virus, and there are 3 Nobel Prizes associated with this chicken virus. So in 1909, 1911, a scientist named Peyton Rouse, he was a microbiologist. He was actually called upon by a poultry farmer, a chicken farmer. And this chicken farmer actually called Peyton Rouse, who was working at Rockefeller in the US at the time. And the chicken farmer said, Dr. Rouse, my chickens are getting tumors. And it's like a pandemic. All the chickens are getting it in an infectious manner. And that was weird. And so Rouse went over to the poultry farm and he took out the tumor. You can see the chicken tumor right here. It's a solid mass. And on the leg, it was actually a malignant sarcoma. That's on the muscle. So he took the tumor out, he dissociated the tumor and sent it through sieves. Sieves are like filters, wherein you would have a very tiny sleeve that will remove all the bacteria from the system, a little bit bigger sieve that will remove all the cells from the system, and then you're going to have a fluid. And Peyton Rouse actually thought, in fact, everybody at the time thought that virus is the cause for cancer. Because at the time, virus was the big thing. And they were trying to treat the viral diseases anyway at the time. So he sieved through the cells, got rid of the cells, the bacterial cells and the animal cells, and then he took the fluid and injected it into another chicken, and the chicken had a tumor. So of course, it was established that cancer is caused by a virus. But then there was an issue. Although chicken virus was infectious, you could clearly see it was spreading from chicken to chicken like a virus. But however, in humans, it was never like that. It was never like a viral pandemic. Like in a family of 5, you would have one person with cancer, the other 4 would not get the same cancer. So the question was, is it really viral? Is the human cancer viral? Of course, the answer is no. However, the pro-virus theory actually led to the establishment of a gene. I'm going to tell you what that is in a moment. So you can see this SARC, SRC, it's a short of sarcoma. And this was a gene that's actually causing the cancer. And this was the first time a gene was identified to cause cancer. And now, although the discovery of Peyton Rouse was in 1911, in 1966, it took a long time for him to establish that a virus was causing cancer, but he eventually got the Nobel Prize in 1966. And then the saga continued with SARC. In 1975, it was again awarded a Nobel Prize for the discovery of how the SARC gene was causing cancer. And this was shared between Dave Baltimore, Renato Dabecco, and Howard Temin in 1975. Then in 1980, another group of scientists at the Salk Institute in San Diego actually discovered the function of SARC, like not just how it forms cancer, but it actually gave the molecular mechanism of how it caused the cancer. And it was found that SARC was a kinase. And kinase is a type of enzyme. I'm going to come to that in a moment. So SARC is a gene that encodes for an enzyme. And this enzyme is super active in cancer, and that's what drives the tumor. And finally, in 1989, Bishop and Barmus shared the Nobel Prize because they drew the entire sketch of how SARC, from the start to the end, was causing cancer. And this cancer was leukemia. So this is the first time uh, what we call a proto-oncogene. An oncogene is a gene that causes cancer. A proto-oncogene is something that's already present in your system, is not cancerous, maintains your cell healthily. However, during cancer, it changes and it becomes an oncogene. And this function of this oncogene was an enzymatic activity, also referred to as a kinase activity. And I'm going to touch upon what that is in a moment. And finally, to complete the full circle, in 2006, Pfizer, the pharmaceutical company, actually came about with a molecule called dasatinib that got approved for the treatment of leukemia. And dasatinib actually binds to SRC and inhibits its kinase activity. So it kills the SRC activity and thereby reduces leukemia in patients. So this is a small story of how the first identified gene was found to have an activity that led to leukemia formation, and then it was successfully targeted by a small molecule, a chemical, that led to reduction of leukemia, especially in pediatric and adult patients. So finally, just to establish the fact that it was not a virus that's causing cancer, but in fact, it was the DNA within the tumor cells that causes cancer. DNA is where all the genes are accumulated. Genes are present in the DNA. There are about 20 to 30,000 genes in the human genome, and it comprises of introns and exons. I'm not going to go into the details of that, but it is the DNA that codes for these enzymes, which could be normal or cancerous, that could define the fate of the cell. So what scientists did in the 1970s is that they chemically made normal cells cancerous. They took out the DNA from those cancerous cells and then they put them back into normal mouse cells again. And when this cancerous DNA was put back into normal cells, the normal cells became cancerous. And then when these cancerous cells are put onto mice, you could see the mice started forming tumors. So this is how we started making an animal model to treat cancer. So now we have a whole mouse with a tumor, and you can actually test new drugs on these mice, and they understand whether the drug is going to be reducing tumor or not. So it was a way to discover new therapeutics. So what are these oncogenes and proto-oncogenes? So proto-oncogenes are those genes that's present in every one of us. Those are normal genes which make sure that when the old cells of your body die off, new cells are made. New cells are able to proliferate. They grow normally, they develop and give rise to new daughter cells. That's the job of proto-oncogene, normal housekeeping. However, in specific cases, which could be environmental or genetic, these proto-oncogenes can harbor mutations. And when these mutations happen, their whole coding system changes. And so when this coding system changes, it no longer remains the healthy, normal gene, making sure your cells are normal and growing. They start doing stuff which are completely abnormal, and they mutate, they increase in number, they start proliferating where you're not supposed to proliferate, for example. And that leads to the tumor formation. And these oncogenes could be anywhere within the cell. So it could be on the membrane of the cell, it could be in the cytoplasm, it could be in the nucleus of the cell, it could be anywhere. So any cell could harbor a proto-oncogene in any part of its system or its physiology. It could be the nucleus, the brain of the cell. We even found oncogene in the mitochondria, which is the powerhouse of the cell, which many of you might remember from your biology classes. They could be in the cell membrane as well. So they could be anywhere in the cell, in any cell of your body for that matter. So there are two sets of genes, the yin and the yang. The one are the oncogenes I talked about, where a normal cell might have a mutational event, and that leads to, like for example, if you're smoking too many cigarettes, the smoke is going to cause mutations in your lung cells. That's one of the reasons. It could also be that in your family history, you have a mutation in what is called a BRCA gene. If the BRCA gene is mutated in your grandma, your mother's going to inherit it, and you're going to get it, you're predisposed to having breast cancer. So similarly, it could be genetic or environmental, and this oncogenic mutation leads to gain of function of the gene. So a normal SARC becomes cancerous SARC, for example. And then the other side of the oncogene, the tumor suppressors, as the name suggests, these genes are important in maintaining and making sure that oncogenes do not cause cancer. And these genes, what they do is they make sure if they identify an oncogene that, that's mutated, we're going to make sure the cell dies off. So they're going to make sure the cell is automatically separated from the rest of the colony, and it kind of shrinks up, doesn't get the nutrients, and it dies off. That is called cell death, programmed cell death, or apoptosis. Some of you with biological background must have heard this term before. They would undergo apoptosis, and tumor suppressors are the ones which pushes these oncogenic cells to undergo apoptosis. But in cancer, if a cancer forms, then these tumor suppressors actually undergo another set of mutations. And that could be again environmental or genetic. And this mutation would inactivate. So in case of an oncogene, it's a gain of function. In case of a tumor suppressor, it's a loss of function. So if there's a loss of function in the tumor suppressor, it can no longer prevent the oncogenes from being removed from the system. So oncogenes proliferate, the tumor suppressors cannot do anything, and then you have what we call a carcinogenesis, or the first signs of cancer. So here is the same figure I showed you in the first slide, but here I'm going to give you some of the mutations and activations that happen. Just an example, no need to remember this, just an idea of how many events need to take place before a normal epithelium becomes metastatic. So in a normal epithelium to an adenoma to say early, intermediate, late adenoma, we have multiple signaling pathways, multiple genes getting activated. You can see a Wnt pathway gene gets activated in the first stage, and then we have an EGFR gene and a KRAS gene. Both of these genes get activated, and that's when you have intermediate adenoma. There's a loss of activation. That is a tumor suppressor TGF-beta. There's a loss of activation, and then because of that, the accumulation of mutation takes place, and we have the late adenoma. And finally, when you have a loss of function of a very important tumor suppressor, P53, you actually have cancer. So this is how it progresses. Multiple pathways have to have activation mutations or inactivating mutations to finally lead to oncogenesis. So you can understand this is a big hoops to jump. But unfortunately, you can see how common cancer is. Just a small piece of trivia. Breast cancer, when we talk about breast cancer, there are actually 76 types of pathologies in breast cancer. And each of these breast cancer types are completely different from the other. So when one person is completely cured of breast cancer and other isn't, that is because their breast cancers are nothing alike. They are completely different, and they need completely different therapeutics to even being targeted. So you can see how complicated this is. It's not like malaria, where you just have malaria, you're giving quinine and you're good. It's actually a completely different pathological disease. So patient 1 and patient 2 might have completely different pathological outcomes in breast cancer than any of the infectious diseases or those treatable diseases that we know of. It's very, very complicated. So, and among these oncogenes that I spoke about, kinases, that is a class of enzymes I mentioned, like SRC is one of them. So the kinases are one of the largest class of oncogenes identified, and which have been successfully targeted for the treatment of cancer. So this is a very complicated tree, I understand that, but this particular tree, a phylogenetic tree that you see here, is basically all the kinases present in the human body, which have been phylogenetically, evolutionarily stacked. So how close they are to each other and how distant they are from each other. These are all incorporated into this entire phylogenetic. So you can see these blue balls. So these blue ones are the kinases that has been targeted till date. By targeted, I mean there are actual drugs in the clinic that for cancer and other diseases that's been approved for treatment of patients. And out of these 540 kinases, only 19 have been targeted till date. So there's a huge lack of knowledge currently regarding what all the other kinases do and what their functions are. And I'm one of those kinase researchers, and I'm going to talk to you about my work a little bit down the road. So just to tell you what a kinase does. A kinase is an enzyme in your body. It's present right now, and it actually triggers a pathway. By pathway, I mean it's basically a communication pathway, just like a radio. So when something tells the first kinase that, okay, this is cancerous, you need to grow. And so this first kinase is going to relay that information into other kinases, like PI3K is a kinase, AKT is a kinase. And this relay of information is through a phosphate molecule. A phosphate molecule is what is used to transfer this communication channel from the outside of the cell to the inside of the cell. And as this communication goes on towards the nucleus of the cell, that's the brain of the cell, the nucleus is told, okay, this phosphorylation signal, this phosphate signal is coming down. I need to start proliferation. I need to start make sure the cells survive. I need to start thinking of how to spread the cancer. And I also need to start of angiogenesis. Angiogenesis is a process wherein it's a mechanism by which blood vessels are formed within a tumor to feed the tumor more and more metabolites. So this is something that tumor does, hijacks the body and starts making its own blood vessels to feed itself. So this is what the signal mechanism is. It's like a command center which actually relays through a phosphate molecule, as simple as that. Simple natural phosphate, but it's actually doing havoc on this cancer, right? So this is what the kinases do. They trigger signaling through phosphorylation. And that's why scientists have been trying to target this kinase for a long time. So they use inhibitors, which would inhibit the function of this relaying mechanism that they have. They're going to stop this phosphate from transferring, and that could cut the signal early on, and so there's no cancerous formation present from the first place. So what a kinase does, a kinase basically uses ATP. I'm sure all of you have heard of ATP before, adenosine triphosphate. So that's the energy currency of the cell. So that's where the phosphate comes from. It comes from ATP. The kinase takes one phosphate out of ATP and puts that phosphate under the next kinase. And that's what we target. We try to make sure that instead of binding to the ATP, the enzyme is stuck with something that's inert. It would bind very tight. It's not going to allow this phosphate transfer to take place. And that's how you have the signal stopped and would not proceed anymore. So again, this is a complicated slide, but if you look at a kinase, how it looks like. So some of you who have biochemistry before, you would know a protein is made up of either alpha helices or beta sheets. So these are all amino acids which are stacked together in different conformations. And you can see there are two lobes, a yellow lobe and a red lobe. All kinases, all 540 of them have the same structure. They have a yellow N-terminal lobe and a C-terminal lobe. And in between these two lobes, there's a gap where the ATP comes and binds, right? And that's what they do. They bind to ATP and triggers cleavage of one of the phosphate molecules that transfer on to the next kinase. So the idea here is to understand how ATP binds to this particular lobe. So you can see within the kinase, within the protein structure, there are two rooms. Just call them rooms. In one of the room, the big room, the ATP comes and forms bonds. And these bonds are hydrogen bonds. And this ATP comes and forms 3 hydrogen bonds with the big room. And then what the kinase does, they know, oh, ATP is here. Let's cleave the phosphate and transfer it onto the next kinase. So what scientists decided, okay, if ATP binds to the kinase, can we make something that would look like ATP, but would not have the phosphate on it? And that's how the kinase inhibitor was discovered. So would do the same thing. You can see the same ring here, the same 3 nitrogens is actually binding to the kinase. But then what this molecule does, it has another bulky group that would actually bind very tightly to the second group. You know, ATP does not bind to that group. So if this particular molecule is big enough, then it can actually bind to both rooms and be so tightly bound that it's not going to fall off if there's more and more ATP in the system. So this is competitively removing ATP from the kinase. So the kinase would no longer be active, would not be able to take the phosphate, would not be able to take the signaling forward. And this molecule here is actually gefitinib, which is the first FDA-approved drug in 2003 for lung cancer. And it had a huge patient base, and it was a very, very successful drug, still being used in the clinic as of today for lung cancer patients. So here are the FDA-approved drugs that target kinases. So there are about 80 of them till about July 2020. I do not know if any that's come up since then. I need to check which ones have come up. And so you can see over the years, when gefitinib was discovered in 2003, there was a huge boom of kinase inhibitors. And now we have multiple kinase inhibitors, nearly 84 of them in the clinic right now being used. However, a small conundrum still remains that all of these inhibitors actually target largely only those 19 different kinases that I talked about. The other, about 520 of them, are still unknown, and we do not know what they do. So as I mentioned, there are two lobes in a kinase. You can see there's an N lobe and a C lobe, N lobe and a C lobe, N lobe and a C lobe, and they're all three different kinases. This is EGFR kinase, an oncogene in lung cancer, BRAF kinase, which is an oncogene in skin cancer, CDK4, uh, another kinase that's primarily found in breast cancer. And you can see the molecule is docking right in between the N lobe and the C lobe. Again, here the molecule is right here, N lobe, C lobe, molecule right here, N lobe, C lobe. It binds to exactly the same place to inhibit this particular oncogene. And you can see, if you look at survival of patients with gefitinib, you can see normal chemotherapy patients die off very quickly. Whereas when you treat them with gefitinib, you can see that they actually survive much, much better. And that's why it was a blockbuster drug. This is an example of vemurafenib, which is a BRAF inhibitor that's used in the clinic extensively. This is a patient with skin cancer. I think this was melanoma. You can see the pale and the tumors all over the body. 15 weeks of vemurafenib and the patient, the exact same patient. You can see what a remarkably valuable these drugs are. Similarly, when you look at palbociclib, the breast cancer drug, with normal hormone therapy, patients don't do that well. But when you have palbociclib with hormone therapy, then the survival is significantly better. So we have so much better survival in breast cancer patients who are hormone positive. So you can see that kinase inhibitors over the years have been extremely valuable for treating cancer, and it still contributes largely in the survival of patients in this disease. So where do I fit into all of these? So my whole idea was, okay, so these have already been successfully targeted. SARC, EGFR, all these have been successfully targeted. What about the other 520? There are so many kinases. We don't even know what they do. We don't even know which cancer they work with. We have no idea whatsoever. So my focus was, let's look at a completely different tree that's not a part of the tree that's not been looked at. So I looked into this red zone, and there are many reasons for that. I'll come to that later. And so this is another family of kinases. These are called the DYRKs, DYRKs, which Dr. Ganguly mentioned in my introduction. So there are 5 different DYRKs, out of which my interest is DYRK2. Just like EGFR, I mentioned CDK4, BRAF, DYRK2 is another kinase. And you can see that I've been working on it for about 10 years now, 8 to 10 years now, and I have a bunch of papers on this DYRK2 molecule. I practically established its function, its oncogenicity, and also developed a drug, which is going to be, it's preclinical, but it's going to start phase 0 very soon. Just think about what a phase 0 can be. I know you've heard of phase 1, 2, 3 clinical trials. Think of what a phase 0 could be, and maybe let Dr. Ganguly know what you think a phase 0 could be. We'll come back to that later on. Okay. So this is actually a staining slide. I'm going to tell you what this is. So I actually spoke to the hospital in San Diego at the time and asked them what were the different breast cancer patient tissues and whether we could get access to some of those breast cancer tissues going forward. So the hospital gave me about 720 different breast cancer tissues and their adjacent normal tissue. So this is a breast cancer tissue and this is a normal tissue for the same patient. And then I actually used a technique called immunohistochemistry, wherein you can actually add an antibody for the gene of interest. For me, it was DYRK2. Take the antibody and put the antibody onto these tumor slices and normal tissue at the same time, and look for the expression of your gene within these tumor tissue. So when I looked at DYRK2, I found out that when in only triple negative breast cancer, I'll tell you what that is in a moment, a triple negative breast cancer, there was a very dark signal, meaning there was very high DYRK2 present in triple negative. However, the same patient's normal breast tissue did not have as much of an expression. So as you know, oncogenes need to be amplified. They have to go up in level to cause cancer. And here we have a new kinase that clearly has much higher expression in the cancer than in the normal tissue. So I started thinking, okay, so DRG2 could indeed be oncogenic within triple negative breast cancer. That's how we found the link to triple negative breast cancer out of all the different breast cancer tissue types of all 76 different types of breast cancer. So triple negative is a relatively less common. It happens in 10 to 12% of all breast cancer patients. It's disproportionately present in African American and African and Black community. And of course, in India, you don't have a huge incidence of triple negative. There are quite a few, but not as much as the rest of the world. So triple negative breast cancer is called triple negative because it lacks three very important markers. So in a female physiology, especially in the mammary tissue, you always have three very important receptors, and these are the hormone receptors. Hormone receptors for estrogen, progesterone, and Herceptin. Okay, these three are very important standard female physiological receptors present in every breast cell, normal breast cell. But in case of cancer, these three major receptors or major markers are absent. Because of that, hormone therapy does not work. And the only option is mastectomy, meaning very, very invasive surgery. And most drugs fail because there's nothing by which this drug can be taken up into the cells. It's very, very difficult to treat, and surgery is practically the only option. And the triple negative breast cancer very quickly spreads to lungs, to brain, and also to the bone. So it's very difficult to treat as well. So I basically decided, okay, let me see if I culture some triple negative breast cancer cells, and if I were to get rid of DRG2 using genetic engineering. So you may have heard of the very famous technique now CRISPR, which got the Nobel Prize 2 years ago. Jennifer Doudna shared it with Carpentier. So the CRISPR technique is extremely powerful. It can very specifically get rid of the genes of interest from within a cell line. Okay, so I used that technique, got rid of DRG2. So my hypothesis is, if DRG2 is cancerous, then it will drive cell growth, abnormal cell growth. And if you were to get rid of DRG2 from the same cell line, this would lead to the cell line kind of reverting back to normal. That is, it's going to have less growth, it's going to have less proliferation, and thereby DRG2 would actually be a target, right? That's what I wanted to look at. So I used an animal model. Remember, I showed an animal model wherein those transformed cells are put into a mouse and a tumor would form. So I kind of did the same thing. I took a triple negative breast cancer cell line. And this cell line is called MDNB231. It's a very famous triple negative breast cancer cell line used extensively worldwide. And I used CRISPR to knock out DRG2. You can see other proteins are present. This is called a Western blot, a simple Western blot, wherein you look at protein levels. And when I did CRISPR, the protein was gone because the gene is not there, so the protein will not be made. And then the loading, that is other genes, other proteins are present because it's not targeted for those proteins. So the cell lacks DRG2 only. And then I actually put the normal cell that has DRG2 in 6 mice. I put in the CRISPRed out cell line in 6 mice. And then I did an interesting little control experiment wherein I took the knockout, that is the CRISPR cell line, and put back the wild type in. I basically reintroduced. I canceled out the CRISPR. I CRISPRed it, and then I canceled out the CRISPR. So that would be like a rescue, meaning that although it had the knockout, now it's back to normal cancerous again. And then if you look at the data here, just follow with me. The red line is the normal cancer. So the cancer progresses, the tumor grows. When you knock out DRG2, that is the CRISPR cell line. When there's no DRG2 present, you can see the tumor is smaller, is growing slower. And then when I put the DRG2 back into the knockout, it goes back to being cancer again. So when there's no DRG2 present, there is less cancer. And you can see the mice here. If you look closely, there's a tumor right here, the breast cancer model. So there's the tumor in normal cancerous cell line. When you have no DRG2, you can see there is no cancer. The plump tumor is not there. But then when you reintroduce DRG2 back into the knockouts, you have the tumor back again. So DRG2 drives triple negative breast cancer, as simple as that. So I started working on a drug. I looked at various databases. I did a lot of screenings. I talked to chemists. I did a lot of collaboration. And finally, we came up with this new molecule. It looks completely different. Looks like a three benzene ring linked together, and then a thiol extension. And there are a couple of OCH3, which are going to make sure that it's soluble. And then I looked at whether this can inhibit DRG2. It clearly can. So this is called an IC50. So IC50 means inhibitory coefficient 50, which is at a particular, at which concentration of the drug you see 50% loss of activity of your enzyme. So at 13 nanomolar, it's nanomolar. Milli is a 1,000th of a milli is micro. 1,000th of a micro is a nano. Okay. So it's 10 to the power 6 of a milliliter, millimolar. So DRG2 at 13 nanomolar of this drug lost 50% of its activity. And so we did another experiment called a crystallography experiment, X-ray crystallography. So this is DRG2. You can see the same physiology in a kinase, the N lobe and the C lobe. And right in the middle, my drug was making hydrogen bonds. So this was actually directly binding to the DRG2 molecule, inhibiting it very, very potently. And of course, I collected more cell lines from triple negative breast cancer patients. I had 6 different cell lines of triple negative breast cancer. And when I added the drug, and the drug would completely kill these cancer cells significantly. So that, yeah, so we have a win-win situation here, and we wanted to take this further into the animal model. So I did the same experiment again, MDMB231 cells, put that into mice, 12 of them, and then I randomized them. So randomization is a method wherein you blindly tell a third person to separate all the 12 cohorts into 6 and 6, and taking into account the gender, age, and everything. So it's a statistical process to make sure that your data that you get is unbiased. And finally, once the tumors formed, we started drug treatment. We get either the vehicle, that is the placebo, and then we have the actual drug. And you can see placebo or vehicle, the tumors grew like normal, but the moment they got the drug, it flatlined. So the cancer was gone. Again, you can see the plump tumor right here on the mammary glands. And when you have the drug treatment, there was no tumor anymore. So this was a chemotherapeutic option down the road. And of course, what we are doing right now is a phase 0 trial in the US and China. It's a multi-center trial. And if it's successful in the phase 0, we're going to take it forward to phase 1. And finally, the last experiment I did was to make sure that this drug was safe to be delivered. So we actually got patients of multiple myeloma. That's a kind of a blood cancer that's present in the cells are present in bone marrow. So the reason for using the multiple myeloma is because you can get the bone marrow aspirates very easily, the bone marrow tumor cells, and also you can get peripheral blood. So you can compare the potency of your drug against the cancerous cell and a matched normal cell. And it's very easy to collect. We just need a venipuncture to collect blood. So we actually treated my drug with both the cancerous blood cells and the non-cancerous blood cells. And I saw that when you have cancerous cells, which are in brown, they were much more sensitive to the drug than normal blood cells, which clearly suggests that the drug that I've developed is non-toxic. So it can be used in patients with minimum toxicity, and they are going to be specifically targeting the cancer cells. So this is where we are with this drug discovery project. We have a new drug, we have a new target for triple negative, and it's currently starting phase 0 trial. And so hopefully down the road, we do not know whether it's going to be successful or not, but at least what we know is that this option could be actually much more, I would say, streamlined down the road. We might be able to get a much better drug going forward. So this is actually a prototype at present. And that is why a medicinal chemistry group, and this is a collaboration between, I think, Harvard and Peking University, they took my drug and they started modifying it to make it more and more specific, more and more soluble, so it can become more like a drug, like far more potent than a drug. And they've actually discovered another molecule called C17, which is a derivative of my molecule. And that is currently that would probably replace my drug to be the one going into phase 0. So yeah, so that's where the project is, and hopefully will be successful, at least if not completely, partially, and thereby add an option to the plethora of drugs we have for breast cancer, and specifically for triple negative, where it's a major unmet need. So I'm going to stop there, and I'm going to acknowledge a few people who are very, very important to me, and that is my own team at University of Dundee, my postdocs, and my PhD student who's worked really hard to develop the drug discovery project. My previous laboratory, who are still involved in the project, especially the phase 0 trial. That's led by Jack Dixon, who's probably retiring very soon, but the lab members are going to continue the drug discovery program. Our collaborators at Harvard, who developed and streamlined the molecule, which I mentioned, in collaboration with Peking University in China. And then I have an excellent medicinal chemistry group at Sardar Patel University here in Gujarat, who actually does excellent chemistry work for me and helps me develop new molecules to target different forms of cancer. And finally, my funding. So that's the Royal Society in the UK has funded my work. I recently got the fellowship, which is pretty surprising and prestigious. It's called the Future Leaders Fellowship that funds all my work. In the States, I have the NCI, or National Institute of Health, the cancer funding, and finally I had the private funds from the Mary Kay Ash Foundation, which allowed me to start off the project in the first place. And I'm very happy to be meeting all of you, even if it's online, and I'm happy to answer any questions. So please do raise your hand and ask questions. As I said, there's no stupid questions. The only thing that can happen is that I give a stupid answer. So please go ahead and ask any questions that you have. And thank you so much for coming. And hopefully you were able to understand some of the basic concepts from this talk. I know I didn't expect people from so many different backgrounds to join. I was only thinking there would be biological or chemistry students. So I apologize if it was a little bit too over the top for some of you, but I'm happy to answer any questions that you may have. Thank you. Thank you. Hello. Yeah.
Am I audible, sir?
Yes, you are.
Yes, sir. So I was actually really glad to hear you. It was very informative, and actually we are very proud that Bengalis are Indians actually go abroad and carry on such inspiring work there. A moment of a lot of pride. Actually, I am very proud right now. Thank you so much. And the
Thank you.
question I have is, you were talking about your molecule.
Can you come a little further away? I think you're just too loud. A little bit further away, please. Thank you.
Okay. So your molecule, this is DRG2.
Doctor. Can't hear you.
Just hold on. I think Jack is having a problem with the mic.
Right. Okay. That's fine. I have no rush.
You can come over here and speak. Okay. এখানে যত আমার পাশেই বলো
So I was just curious to know that what pathway it is actually blocking. Is it actually blocking the episotic pathway, or is it helping the autophagic pathway? Which pathway is it involved in?
That's a great question, Dr. Jamal. That's really nice. Thank you for that. So this particular enzyme is actually working on the stress pathway. It's called the proteotoxic stress pathway. So DERK2 actually phosphorylates the phosphate transfer takes place on the proteasome, which maintains the protein homeostasis in the cell. That is, the proteasome is like the garbage can. All the old proteins are degraded by the proteasome, and it gives amino acids that can be resynthesized in new proteins. And DERK2, in fact, amplifies the activity of the proteasome, so it starts chewing up the tumor suppressors, and thereby it causes cancer. So that's the pathway it's targeting. It's not the proliferation pathway, the stress pathway, the proteotoxic stress pathway of the cancer. That's what it targets.
So sociotoxic stress pathway, is it involved with the chaperone?
Involved in the
With chaperone.
chaperone. Yes, it is. The HSF1 and the proteotoxic pathway, it's involved with the chaperone, yeah. So it phosphorylates both the proteasome and HSF1 with the heat shock factor 1. The heat shock factor 1 is a transcription factor that drives the HSPs and the chaperones. So yeah, that's what it targets.
Thank you, sir. Thank you.
Yeah.
Okay, for everybody, please feel free to actually ask your questions in Bengali, Hindi, English, whatever questions do you have. You can even write it, type it also.
Yeah, you can type it also, please. You're more than welcome.
Any other questions if anybody has?
Any general questions? Anything?
General questions regarding cancer?
Yep. It's generally very nerve-wracking to ask questions sometimes. So, but
I just have a very general question. So, is there any difference in this?
Hello. So you were talking about zero-phase trial. I would like to share your experience with the students. We have a lot of students with us. Can you just talk about the zero-phase trial with our students?
So is it the question
about the zero-phase trials for the students?
Right. Yeah. So that's an academic development, actually, the phase 0. So as you know, clinical trials are phase 1, phase 2, phase 3. Right? Everyone knows about that. It's phase 1, phase 2, phase 3. But most clinical trials are run by companies or multi-million-dollar companies. So they have the money to invest in a phase 1 that almost costs $5 or $10 million. Okay. So, but in academia, we don't have that kind of money. So what we do, we actually recruit about five patients with cancer, and then we would treat them with the drug to see if there are any side effects, are there any drug interactions going on, is the tumor reducing, and that gives us the encouragement that, oh, it's working and it's not toxic, to actually invest that kind of money to a phase 1. So phase 0 is when you have like 5 or 10 patients and you test your drug to do an MTD, or also referred to maximal tolerated dose. So how much maximum dose can you give? Is it 500 milligram a day? Is it 1 gram a day? Is it 6 grams a day? So that's how we establish that's the phase 0. So that is not registered. It's just a few patients volunteering to take the drug initially. That's a phase 0.
Yeah, I have just a general question actually. It came as a curiosity, out of curiosity. This DYRK2, did you find any expression difference in male and female?
No, actually, no, absolutely not. It's
the mechanism of breast cancer from this particular kinase is same in males and females.
Yes, it's same in males and females, of course. And in fact, in male, and I shouldn't say males. So it's interesting. Like a triple negative breast cancer is not really a female physiology tumor because it doesn't have the estrogen, progesterone, herceptin anyway. So it's a very gender neutral tumor. So because it's such a gender neutral tumor, what genetic alterations that happen in this tumor is not really known. And it happens to be that DRG2 is amplified. And that's why we took this forward. Again, an interesting tumor, I didn't talk about this today, but that's also part of my publication, is multiple myeloma. It's actually a blood cancer of B cells. It's a B cell plasma cell tumor. It happens in both males and females in normal blood cancer, and there, DRG2 is present regardless of gender. So there are specific genetic mechanisms in these two cancers that trigger the amplification of DRG2. We don't understand why that is, but it just happens that way. In a normal tissue, like if I take the tissue of myself or my wife right now and stain with DRG2, it's going to be exactly the same. And it's only when in triple negative tissue do we see this. We also don't know at which stage. Is that adenoma stage, early, late, intermediate? We don't know which stage this comes up in. But it's worth following that up though.
And why are Indians not so predisposed to this triple negative?
That's firstly, it's probably the population that drives it, and also the lack of screening. So it's probably that some patients are triple negative, but once the physician sees the breast cancer, starts on the same chemotherapy as any other tumor. That's common. Whatever data is available, the epidemiological data that's available, that's telling us that Indians are less than 8% breast cancers across the whole spectrum. Whereas in the African American community in the States, it's nearly 20%. Okay. So it could be the differences in epidemiological data, or it's just because there's some genetic reasons why, or specific mutations that Indians don't have, that are environmental factors that Indians don't have, or it could be turmeric eating that we do. It could actually be more protective. But at this point of time, I'm a little skeptical about Indians having less triple negative, because that's an outlier compared to the rest of the world. But that's just because we don't have enough data to support that at this point of time. But all we know right now is 8% or less than 8%.
Because it's interesting in the fact, because all my relatives who have had this breast cancer, they were all triple negative.
They were all, yeah. I mean, again, you're looking at a small cohort, and probably they were triple negative. But then, as I said,
Yeah, I mean, people who I know, Indians, my aunts and everybody, and they're all they recovered, they fought brilliantly, and some of them even
look,
expired.
that's
But
right.
all triple.
Yeah, any cancer,
But we are less.
yeah. So any cancer that's at stage 3 or lower are treatable. Doesn't matter whether it's triple negative or not. It's only when it becomes metastatic that it starts invading into the other tissue and spreads. That's what's going to kill. If the tumor was reached at the right time, it will not lead to fatality. Because surgery.
Our research and development convener, Dr. Subhashri Sarkar, he has got a question.
Yes,
Subhashri, please go ahead.
Yes, sir. Am I audible?
yes, you are.
Yes, sir. Thank you, sir, for your wonderful presentation. It was really enriching. Sir, actually, I would like to share an information. My father was diagnosed with light chain amyloidosis, and he eventually expired due to that. And we were told that we came to CMC Vellore, and we have been to Apollo Chennai, and we have been to many, and we have seen in India, I think you will be hearing about Dr. Maman Chand. He is a renowned hematologist. So we couldn't meet him. He's the number one. We met number two hematologist in Apollo Chennai, and we had a treatment plan for him. And they suggested that multiple myeloma and light chain amyloidosis are closely related, and since that amyloidosis has no direct treatment, so he went on he was given bortezomib and dexamethasone. So these were the bortezomib and dexamethasone were given, and I also found on the internet that it is the most preferred available treatment right there.
Yeah.
But unfortunately, the plan didn't succeed, and he succumbed. So I would like to know whether your molecule, whatever you are being discovering, and these things can be targeted to multiple myeloma and kind of those diseases, or is it something else?
So light chain amyloidosis is a very, the problem is it's a very general term. It's something like the adenoma I talked about in solid tumors. Okay, it's a stage where there could be cancer, there may not be cancer, or it could be pretty full-blown cancer. And because there are the detection mechanism that we have, it only looks at 2 or 3 different genes, and then they say the pathology is this, based on the best educated guess. Okay, there's no other better way than a best educated guess to tell you there's an adenoma early, late, intermediate. Similarly with some of the MGUS phenotype, which is the mammalian gammopathy of unknown significance, amyloidosis, beta chain amyloidosis, is basically wherein the antibody numbers in the blood is very high. That's what it is, very high number of antibodies in the blood. And if there's too much antibody in the blood, and since B cells secrete antibodies, so there's a problem with the B cells. Okay. And so the best treatment for any B cell related malignancy, not just cancerous, any neoplastic malignancy, is using bortezomib. And bortezomib is the proteasome inhibitor, the first in class. And DIRC2, in fact, is synergistic with bortezomib. If you put the DIRC2 inhibitor with bortezomib, it's going to kill those cells 10 times faster than bortezomib on its own. Dexamethasone with it is more for, I would say, it's a steroidal drug, dexamethasone. So it's going to help in making sure that the cells are also dying at the same rate. But bortezomib with dexamethasone is only twofold. but that's what's approved. DRG2 inhibitor with BOTA2 is tenfold. So my drug, unfortunately, is going to come out late if it at all does. But one thing I can tell you that from patients like your own father and many other patients actually contributed to the development of this drug. Their samples are what allowed us to understand the mechanism and thereby contribute to making better therapies in the future. So in hindsight, if you say that maybe in 5 years' time, my drug would probably make it if I'm super lucky and everything works out, then it would have a new option for patients with beta amyloidosis as well, not just
Okay.
myeloma. But we look at the worst case scenario. But if the worst case scenario works, the others are going to be too. If I can ask a quick question, the bortezomib and dexamethasone treatment is generally effective. So why did what happened?
So actually, what happened? I will just tell you the entire details. So my father was suffering for prostate problem for around 20 years. So he was taking some prostate kind of a drug. So unfortunately, that one day there was gross blood leakage from due to that urine. And so we rushed to the hospital, and they said that you need an immediate removal of that prostate entirely. So
Right.
after that prostate removal was done, unfortunately, we found that his entire body got swollen with water.
Hmm.
So the urologist who did the operation in Ruby Hospital, he was also shocked to see that why isn't that water filling is there, and why is the amount of water which is accumulated in his body is not coming
Hmm.
out. So
Hmm.
then he found that the protein content in his muscles is really less. So we were told that since the protein content is less in the muscles, so the muscles cannot squeeze to bring out the water from the from that body. So he was given protein injections, but still also it didn't work. So we came from Ruby Hospital to Apollo Chennai, and then it was diagnosed through because up till there also the creatinine and the uric acid levels, the kidney was performing fine. After we came to Apollo Chennai, he was suggested a biopsy of the kidney and bone marrow biopsy. After that, we were told that he is having that light chain amyloidosis, and that with I think beta or say link something was there. It is around 3 years back, so I don't remember much. So and then we were told to start a chemotherapy session. So while doing the chemotherapy session, he in the first stage he responded well, and in the second stage also he responded well in South India. So after that, since we are already staying here for 3-4 months, we have exhausted our funds, and I wanted to get back to Kolkata because he was taking only chemotherapy. So we went back to Kolkata and we admitted him to Tata Medical Center in there. So there he was under Dr. Ravakan Bhave and Dr. Sourav Bhave. He was under Dr. Sourav Bhave there, and he was receiving the treatment. So unfortunately, there when we came back to Kolkata, he was responding very well. But in Tata Medical Center, one fine day, because I went back to college, and when I came back, I went back to the college for joining, and I was called back. They told me that your father is having some breathing issues. So when I got back there, I found that my father is having a fever, and my father told me that he was kept under PET scan for around 4 hours without any blanket or something like that. So he got cold. So because he was already immunocompressed and he got cold, he was kept on oxygen. So there suddenly his entire health got deteriorated, and he eventually succumbed due to this side effect of the amyloidosis, but mostly due to it was written that some shock, and it is basically an hospital acquired pneumonia. So he
Right.
acquired pneumonia, and then he was succumbed to that, but he was
Yes,
responding well to the therapy.
I understand that. Yes. So generally, most hematological conditions are immunocompromised is one of the biggest issues whatsoever. Immunocompromise is B cell malignancy would lead to reduction in B cell numbers. It will affect the T cell numbers. So that's probably an infection related issue rather than the amyloidosis or the drug treatment. So
Yeah, the drug treatment was quite well. It was my father was responding well, and when one day only I just left him alone, and he on that day, very day when I was leaving, I saw him taking chicken and rice very 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 very. He was very happy. মানে খুব ভালোভাবে উনি মাংস ভাত খেলেন, আমাকে টাটা করলেন, ভাই তুই যা, তো 3 মাস ধরে নষ্ট হতে সময় তুই কলেজে গিয়ে জয়েন করে আয়। And when I came back, he was undergone PET scan, which I don't know, I was not informed also. And he told, my father told that, আরে আমার স্ক্যান করলো, আমাকে একটা কম্বলও দেয়নি, আমার ঠান্ডা লেগেছে। So he got cold, and that was severe cold, and after that the entire thing was downwards only.
Downwards for that's very unfortunate to hear, but yeah, these are the kind of cases where I mean any drug, it's very tough to say what drug is going to work and what not. কি জন্য সেটাও বোঝা মুশকিল। It's very
So
unfortunate.
আমি তখন মানে আমি ততদিন পর্যন্ত বাবা কখনো অক্সিজেন সাপোর্টে ছিলেন না। তারপরে আমি এসে পরে দেখছি বাবা অক্সিজেন সাপোর্টে আছেন, তারপরে বাবাকে ওই মরফিন দেওয়া হচ্ছে, আমি তো মানে পুরো হয়ে গেলাম।
আপনার যদি আরো প্রশ্ন থাকে আপনি আমাকে ইমেল করুন, আমি আমাদের দিক থেকে আপনাকে কিছু কিছু আরো প্রশ্ন উত্তর দিতে পারবো। But thank you so much for sharing.
হ্যাঁ স্যার, আমি আপনাকে ইমেল করব, I will just respond. Sir, presently I am also in Vellore for my mother's treatment. I will get back to my home and I will আমি ওগুলো বের করে দেখবো যে ফাইলগুলো ছিল পুরোনো কেস স্টাডি গুলো, তো আপনাকে পুরো স্ক্যান করে আপনাকে পাঠাবো।
I'm more than happy to look at them. Thank you.
Yeah. Thank you, sir. Thank you so much.
Any other questions?
Any other questions? If there are no questions, then I would request
One
Dr.
question.
Zaka Jamal to.
No, there's a
Olukta.
question.
Yeah, please go ahead, Shashwati.
Yes, Onupta, I have a question. I have a question to Sourav, whatever. Hi. Good afternoon. Actually, I have a similar question like that of Shubhati. আমি বাংলাই বলছি, since you are a Bengali. ব্যাপারটা হচ্ছে, his case was with his father. Unfortunately for me, it's with my mother. And last year, my mother has been diagnosed with GIST. matlab
gastrointestinal
exactly, gastrointestinal stomal tumor. তো we took her, আমরা মাকে এতে নিয়ে গেছিলাম টাটা মেমোরিয়াল, যেটা মুম্বাই, এবং মুম্বাইতে ইমাটিনিব বলে একটা যেটা সিক্রেট যেটা আছে, ট্যারোসিন ওই কাইনেজ, ওই একই জিনিস যেটা আপনি বোঝালেন, ওই মেডিসিনটা দিয়েছিল। এবং ওনার ওরালি 1 year, মানে লাস্ট সেপ্টেম্বর থেকে এই ডিসেম্বর অব্দি 1 year ইমাটিনিব চলে।
ঠিক আছে।
And this December 24th we got her operated. Okay, this year, মানে just last year 24th হয়েছে। তো বাট আমার একটা প্রশ্ন ছিল, which the doctors unfortunately failed to satisfy me, or maybe he gave any other explanation. ব্যাপারটা হচ্ছে, যখন ওষুধটা খাচ্ছিলেন তার সাথে সাথে আমার মায়ের মুখে ইডেমার মতন হয়ে গেছিল, মানে পুরো মুখটা ফুলে, বিশেষ করে লোয়ার যে আইয়ে যে লোয়ার আইলিডটা ওখানে, চিকসে, ইভেন হ্যান্ডসে ভীষণ রকম, মানে ওটাকে ইডেমাই বলে, মানে ওয়াটার ফিল্ড ওরকম হয়ে গেছিল। এবং মুখটা রীতিমতো, মানে যদি ডায়ামিটার সাপোজ থাকে কোনো কিছু 2 সেন্টিমিটার, ইট রিয়েলি বিকেম 4 সেন্টিমিটার লাইক দ্যাট, মানে একদম ডাবল হয়েছিল। উইথ ইচিং, নাও ইচিং, the doctor said that itching will be there, and they gave certain medicine, symptomatic medicine দিয়েছিলেন। বাট ইডেমা, this is the question, যে why, এই যে আমি শুনলাম আপনি ইডেমার এটা বললেন, কিন্তু আমি জাস্ট এটা একটু ক্লিয়ার একবার আপনার কাছে জিজ্ঞেস করতে চাইছি যে এই জায়গাটা কেন। এবং আরেকটা প্রশ্ন, এই যে মেডিসিন, এই যে ইমার্টিনিব বা ইমার্টিনিব জাতীয় যে টার্গেটেড যেই ড্রাগ গুলো, এগুলোর জন্য কি কোনোভাবে নিউরোপ্যাথির সাথে রিলেটেড আছে?
বলছি আমি,
বিকজ কেন বলছি, আমার মা ইনসিডেন্টালি মার্চ মাসে বিছানা থেকে, মানে বেড থেকে পড়ে যান। পড়ে গিয়ে ওনার একটা সার্জারি হয়, যেটাকে আপনি TILS সার্জারি বলে, মানে প্লেট, স্পাইনে যে প্লেট বসানো, সেটা হয়। কিন্তু তার যে ড্রাগে অন্য পেশেন্টরা যেভাবে রেসপন্ড করে, ইজিলি ওয়াক করে, মানে ইজিলি ওয়াক আউট করতে পারছে, এভরিথিং ইজ নর্মাল, মায়ের বেলায় কিন্তু সেটা আমি দেখছি না। অ্যান্ড দ্যাট ইজ হোয়াট মাই কোশ্চেন ইজ, যে কোনোভাবে এই ড্রাগটার সাথে কি নিউরোপ্যাথির কোনো রিলেশন আছে?
ওকে, ইমাটিনিবের আমি একটা ছোট্ট হিস্ট্রি বলছি আপনাকে, কারণ ইমাটিনিব ড্রাগটা অ্যাকচুয়ালি তৈরি হয় ডান্ডি কোলাবোরেশনে। ইমাটিনিব ড্রাগটা ইজ দ্য ফার্স্ট কাইনেজ ইনহিবিটর এভার অ্যাপ্রুভড। 2001 সালে অ্যাপ্রুভ হয়েছিল ইমাটিনিব। ইমাটিনিব প্রাইমারিলি টার্গেট করে হচ্ছে একটা, জাস্ট লাইক আমি ইজিএফআর কাইনেজ বললাম, ওরকম একটা 3টে কাইনেজ আছে, পিডিজিএফআর, কিট আর ফ্লেট, একই ফ্যামিলির 3টে। তো এই 3টে কাইনেজ ইনহিবিটর, দ্য প্রবলেম উইথ ইমাটিনিব হচ্ছে, ইমাটিনিব যখন প্রথম আবিষ্কার হয়, ডানবিতে আবিষ্কার হয়ে সেটা নোভার্টিসের কাছে যায়। নোভার্টিসের তখন সিবাগাইজি নাম ছিল। নিক লিন্ডেন বলে একজন সায়েন্টিস্ট, উনি এই ইমাটিনিবটা কুকুরদের মধ্যে টেস্ট করছিলেন, কারণ প্রথমত অ্যানিমাল টেস্টিং হয়, তো কুকুরদের তো ব্লাড ক্যান্সার হয়, আর ব্লাড আর জিস্টের জন্য এই ড্রাগটা ইস্যু হয়েছিল। প্রবলেমটা হচ্ছে কুকুরদের মধ্যে ভেরিয়াড লেভেলস অফ টক্সিসিটি দেখা যায়, বুঝলেন তো, বিভিন্ন, এবং ইডেমা ওয়াজ ওয়ান অফ দ্য। ফুলে যাওয়াটা ইজ নর্মাল, ফুলে যাওয়াটা হচ্ছে ইটস নট ফেটাল সিনারিও, কারণ ফুলে যাওয়াটা এই কারণেই হয় কারণ একটা ইমিউন রিয়াকশন হয়। আর এই ইমিউন রিয়াকশনটা তখনই হয় যখন when a person's tumor is starting to recruit immune cells within itself. ইমিউন সেলসের কাজ হচ্ছে গিয়ে কোনো ফরেন বডিকে মেরে ফেলা, কিন্তু ক্যান্সার কি করতে পারে, ইমিউন সেলস গুলো যখন এসে ওকে মারবার চেষ্টা করে, ওদের ভুলিয়ে ভালিয়ে নিজের মধ্যে নিয়ে নিতে পারে। and uses the ঘরশত্রু বিভীষণ যাকে বলে না, it is the perfect example. ওই ইমিউন সেলস গুলোকে টিউমারের মধ্যে নিয়ে তার ভুলিয়ে ভালিয়ে starts working for the tumor. আর when this happens, বডির ইমিউন সিস্টেমটার মধ্যে একটা সিভিয়ার টার্মোইল তৈরি হয়, আর as a result ইডেমা, ইচিং, রেড প্যাচেস, তারপর হচ্ছে র্যাশেস, সুপার 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 কম। ইডেমা এটা হতেই পারে। প্রবলেমটা একটা যেটা আপনাকে আমি বলতে পারি সেটা হচ্ছে বেটার জিস্ট ড্রাগস কিন্তু আছে, ওকে, which is more specific for PDGFR, like nilotinib আছে, avapritinib বলে একটা ড্রাগ বেরিয়েছে যেটা এখন জিস্টের জন্য ব্যবহার হচ্ছে, কিন্তু প্রবলেমটা হচ্ছে কোনো ডাক্তারই না এই ভালো ওষুধটা আগে দেবে না। তার মেইন কারণ হচ্ছে না না না, এটা কিন্তু রিজন আছে, এটা আমরাও সেটাই বলি করতে, বেটার ড্রাগটা যদি সে আগে দিয়ে দেয় রেজিস্ট্যান্সটা অনেক তাড়াতাড়ি কিল করবে, কারণ অ্যাভাপ্রিটিনিবের ওপর না কোনো ওষুধ নেই। তাই যদি আপনার মাকে ওরা অ্যাভাপ্রিটিনিব দিয়ে দেয় এবং উনি হয়তো 1 মাসের মধ্যে সুস্থ হয়ে গেলেন, তারপর ফর এনি রিজন যদি জিস্ট ফেরত আসে আর কোনো অপশন নেই, বুঝলেন তো, সেই জন্য ইমাটিনিবটা দিয়ে শুরু করাটা কিন্তু বাঞ্ছনীয়।
Now, one more thing. Since it is being operated, now 24th it's being operated and she is being stopped. Okay, imatinib এখন stop আছে and the doctor has suggested that they will again start for this imatinib and it will continue for 3 years. Okay, এবার ব্যাপারটা হচ্ছে এখন আমার মা is normal, মানে after the surgery her face, facial features, everything is normal, no edema, no nothing, মানে একদম নরমাল মানুষের মতো টাচুড। থিং ইজ দ্যাট আই ফিয়ার যে আবার যখন তাহলে ইমাটিনিব নেক্সট টাইম যখন আবার চালু হবে, তো তাহলে কি আবার সে there is a chance of getting that edema and all those things, right?
Yes, there is, but there is a chance, কিন্তু এটাও দেখতে হবে তখন যে এখন we already know কি ওনার মধ্যে টিউমার হয়েছিল এবং ওই টিউমারগুলো যে ফেরত আসে সেগুলো তাড়াতাড়ি ধরা পড়বে, কারণ এখন আর ওই পার্টিকুলার সাইজে 2 মিলিমিটার 5 মিলিমিটার না হয়, আপনি হয়তো 1 মিলিমিটারের মধ্যে টিউমারগুলো ধরা পড়ে যেতে পারে। আর যদি টিউমার ছোট থাকে ইমাটিনিবের ডোজও কম হবে।
না, টিউমারটা অপারেট হয়ে গেছে, মানে ইট হ্যাজ বিন ফুললি রিসেক্টেড।
হ্যাঁ, টিউমারটা অপারেট হয়ে গেছে, কিন্তু
বাট ও আচ্ছা
রেকারেন্সটা বেশিরভাগ সময়ই হয়। এটা কিন্তু মানে অন্য টিউমার যেমন খুব ব্রেন যেমন খুব খারাপ, জিস্টের ক্ষেত্রে না আপনার লাইফ স্প্যানটা অনেক দিন মানে পুরোই থাকতে পারে এই ওভার দ্য টাইম, বিকজ দেয়ার সো মেনি অপশনস দেয়ার, জিস্টের অনেক অপশনস আছে। এটাই এই সার্জারি করে যে টিউমার গুলো বেরিয়ে গেছে, টিউমার গুলোর জায়গাটা না পুরোটা কেউ বার করতে পারে না সবসময়, লাকিলি অনেক সময় বেরিয়ে যায়। আশা করছি
they did the sleeve gastrectomy, মানে ওই জায়গাটা স্লিভ করে দিয়েছে,
জায়গাটা পুরো সরিয়ে দিয়েছে, কিন্তু আসলে জিনিসটা কি জানেন তো, এগুলো ভীষণ রক্তের মধ্যে দিয়ে ভীষণ ইনভিজিবলি ছড়াতে পারে।
আচ্ছা,
বুঝলেন তো, অবশ্য আমি আগেন বলছি, দেখুন জিস্ট কিন্তু ওয়ান অফ দোজ ক্যান্সার যেটা কিন্তু খুব অনেক ভালোভাবে ম্যানেজ করা যায়, খুব
ওটা বলছিলেন ওনারা,
এটা খুব ভালোভাবে ম্যানেজ করা যায়। আমার কথাটা হচ্ছে এই ইডিমা যে জিনিসটা এটা কিন্তু ঠিক হয়ে যাবে, মানে ওটা ইটস নট ফেটাল, ইডিমা ইজ নট ফেটাল, দেখতে খুব খারাপ, দেখতে ভয় লাগে, বাট ইটস নট আ সুপার ফেটাল সাইড এফেক্ট, ইট ইজ আ সাইড এফেক্ট বাট ইটস নট আ ফেটাল সাইড এফেক্ট। আরেকটা যেটা হচ্ছে ইমাটিনিবটা আমি ভরসা করবো এই কারণে, কারণ উনি যদি ইমাটিনিবে রেসপন্ড করেন না, অন দ্য রোড ওনার অনেক অপশন আছে।
হ্যাঁ, ইমাটিনিবে রেসপন্ড করেছে বিকজ ইট ওয়াজ অ্যাকচুয়ালি 10 সেন্টিমিটার, ইট বিকেম 7.5 সেন্টিমিটার।
আপনি জানবেন ইমাটিনিবে যদি আপনার মা রেসপন্ড করেন, there's a very very good chance উনি ওনার পুরো লাইফ টাইম কাটিয়ে দিতে পারবেন।
Okay. And the link with neuropathy, anything? I just
Neuropathy দেখুন different people মধ্যে neuropathy different reasons হয়। শুধু ইমাটিনিবের জন্য যে নিউরোপ্যাথি হচ্ছে এরকম কিন্তু কখনো সবসময় হয় না। অনেক সময় অনেক কিছু এক্সট্রা আসে, যেমন ফর এক্সাম্পল ওনার যে ইডিমাটা হয়েছে তার জন্য যদি বেশি ওয়াটার রিটেনশন কিডনির মধ্যে হয় তখন দ্যাট ক্যান অ্যাকচুয়ালি লিড টু
no, her KFT is normal and all those things
বাট
are
আমি
normal.
জাস্ট বলছি অনেক ডিফারেন্ট রিজন নিউরোপ্যাথি হতে পারে। আরেকটা জিনিস যেটা সরি
ডায়াবেটিস এর জন্য নিউরোপ্যাথিটা
ডায়াবেটিস ইজ আ রিজন।
Okay, yeah, she is diabetic.
ডায়াবেটিস হ্যাঁ ডায়াবেটিস যদি থাকে তাহলে দ্যাট ইজ আ মেজর কোমরবিডিটি একটা বলতে পারেন। ওটা হলে
she is
কিন্তু
diabetic.
নিউরোপ্যাথির জন্য খুব হাই হতে পারে, কারণ একটা জিনিস জানবেন টিউমার ফিডস অন গ্লুকোজ।
Yeah,
টিউমার ফিডস
just like normal cell.
এই জন্য যদি ডায়াবেটিক হন তাহলে কিন্তু দে উইল ফিড অন দ্যাট। আরেকটা হচ্ছে মেনি অফ দিস kinase inhibitors they often affect a type of kinase called PI3K. PI3K ডায়াবেটিক পাথওয়েতে রোল প্লে করে। ওখানে ডায়াবেটিস there are many things to be considered by the physician. আমরা তো ওয়ান ডিরেকশনাল ভাবি, কারণ আমরা ওই কাইনেসটাকে দেখি, টার্গেট করি, সেল দেখি, ইঁদুর দেখি, তারপর মানুষে যাই। কিন্তু ডাক্তাররা না এই জিনিসটা, উনি যদি ইম্যাটিনিব বলে থাকেন টাটা মেমোরিয়াল সেন্টার থেকে, যদি ইম্যাটিনিব আর আপনার মা যদি ইম্যাটিনিব বারিং অল আদার কোমরবিডিটিস, বারিং অল আদার রাশনাল, শুধু বলি জাস্ট উইথ ইম্যাটিনিব, উনি যদি এটা রিঅ্যাক্ট, উনি যদি এটাকে
পজিটিভ ফিডব্যাক এসছে,
ওনার প্রচুর অপশনস আছে এবং it is a good chance she will have a full life.
Thank God, something like
as I said, there are many other factors in it. So আমার কথাটা একদম golden words হিসেবে নেবেন না।
Yeah, I will consider this to be a golden word actually, because I'm a bit relieved.
কারণ ইমাটিনিব তো আমার লম্বা কাজ আছে, ইমাটিনিব, অ্যাবোফ্রিটিনিব, নিলটিনিব, এগুলো সব নিয়ে আমার কাজ।
Can I mail you personally if I want to know something later? Yeah, thank you. That would be so kind.
No problem.
Thank you.
সাকসেসফুল আছে আমাদের ডিপার্টমেন্ট অফ জুওলজি ফ্যাকাল্টি।
আচ্ছা নাইস টু মিট ইউ।
Thank you.
আশা করি পারলে আমি পার্সোনালি আসতে পারবো, এবার আসতে পারিনি।
সেটা খুব ভালো হবে, তখন মানে আরো অনেক কিছু ডিসকাস করা যাবে মানে।
আর কোনো প্রশ্ন?
Talk was informative. I was actually listening to it.
আদিত্য,
আদিত্য বলো, কোশ্চেন জিজ্ঞেস করো।
From where you have got the LDN molecule and how much time it had taken to know that it have satisfactory effect?
ইন্ডিয়ান মলিকিউল,
এলডিএন মলিকিউল।
আরেকবার প্লিজ রিপিট করুন। বাংলায় বলো।
বলছি এলডিএন মলিকিউলটি আপনি কোথা থেকে পেয়েছেন আর আপনি মানে কতটা সময় এর উপরে দিয়েছেন যে এলডিএন মলিকিউলটা যথেষ্টভাবে কাজ করছে?
এলডিএন মলিকিউলটা আমি কোথা থেকে পেয়েছি? আচ্ছা, একটা পার্টিকুলার ওয়ে অফ সার্চিং ফর মলিকিউল হয়, তার মধ্যে দুটো টেকনিক আছে। একটা হচ্ছে স্ক্রিনিং, একটা বড় লাইব্রেরি অফ মলিকিউল থাকে আর সেখানে তুমি তোমার কাইনেজ অফ ইন্টারেস্ট এনজাইমটাকে মলিকিউলের উপর, বিভিন্ন মলিকিউলের উপর দিয়ে এখানে আসে করতে পারো কতটা অ্যাক্টিভিটি পড়ে আছে, এবং যেটাতে অ্যাক্টিভিটি থাকবে না সেটাই তোমার টার্গেট, সেটাই তোমার ফার্স্ট স্টেজ। তো সেইটা দিয়ে আমরা 1.7 মিলিয়ন কম্পাউন্ডস এর একটা লাইব্রেরির মধ্যে দিয়ে এটাকে নিয়ে যাই, and from there we got about 2573 হিটস। তার থেকে আমরা শর্টলিস্ট করে we identify 3, আর এই তিনটের মধ্যে একটা ছিল এলডিএন। আর এলডিএনটা অ্যাকচুয়ালি আমরা যেটা দেখি সেটা হচ্ছে ভেরি সলিউবল, মানে জলের সঙ্গে মিশে যায়, আর যেহেতু জলের সঙ্গে মিশে যায় সেই জন্যই এটাকে আমরা আগে নিয়ে যাই। মাঝখানে একটা স্টেপ আছে, তুমি হয়তো আমার ইন্ট্রোডাকশন দেখেছো, আমি কারকিউমিন নিয়ে কাজ করেছিলাম, টার্মারিক ডেরিভেটিভ। তো আমি ওটার মধ্যে একটা কারকিউমিনের এলিমেন্ট ইন্ট্রোডিউস করিয়েছিলাম। ওই একটা পার্টিকুলার যে এক্সটেনশন আছে এস সালফার থেকে এক্সটেন্ড করছে, ওটা কারকিউমিনের একটা অ্যাক্টিভ কম্পোনেন্ট। এই দুটোকে ইন্টিগ্রেট করে এলডিএন মলিকিউলটা তৈরি হয়, এবং এলডিএন মলিকিউলটা আমরা ওভার এই কাজটা আমি শুরু করেছিলাম 2017 থেকে। তো 2017 থেকে জিনিসটা কারকিউমিনটা প্যারালালি চলেছিল, দুটো মিলিয়ে এই পেপারটা বেরোয় 2019-এ। তো 2019-এর মধ্যে আমরা প্রি ক্লিনিক্যাল সব কমপ্লিট করেছি, কিন্তু তারপর আমি যেটা মেনশন করলাম এই মলিকিউলটাকে আরেকটু ইমপ্রুভমেন্টের প্রয়োজন ছিল, কারণ মানুষের মধ্যে দিতে গেলে আরো ইমপ্রুভমেন্ট লাগে। ইঁদুর তো অনেকবারই ক্যান্সার মুক্ত হয়েছে, কিন্তু মানুষকেই করাটা আসল। তো সেই জন্য আমরা এই পার্টিকুলার মলিকিউলটাকে আরেকটু মডিফাই করেছি 2022-তে, সেটা ই লাইফ পেপারে বেরিয়েছিল, যেখানে ওরা একটা মডিফাইড ফর্ম তৈরি করে। সেটার পর এখন ওইটা হিউম্যানের মধ্যে যাবে, এই প্রবাবলি এন্ড অফ দিস ইয়ার আমরা ওটা হিউম্যানের মধ্যে দেব at the phase 0 level, 5 জন পেশেন্ট, 5 থেকে 10, আর তারপর জানা যাবে জিনিসটা হচ্ছে কি হচ্ছে না। তবে এখন আমি এই পেশেন্ট লিঙ্কে আমি ইনভলভ নেই আর, কারণ আমি এই প্যাটার্নটা দিয়ে এসেছি ওদের। I just wanted this out of the way, কারণ আমি অলরেডি ওটা আমার পোস্ট ডক্টরাল টাইপ অফ ওয়ার্ক ছিল, তাই আই ডোন্ট ওন দ্য ওয়ার্ক, মাই সুপারভাইজার ডিড। সেই জন্য আমি ওটা ওদের দিয়ে এসেছিলাম, সো দে আর এবল টু টেক ইট ফরওয়ার্ড ইনটু দ্য ক্লিনিক। হ্যাঁ, তবে এটা ঠিক, যদি এটা অ্যাপ্রুভ হয়ে যায় আমার রাইট আছে ওটাকে লাইসেন্স করে ইন্ডিয়াতে একটা প্রাইস which would be agreeable with the ministry, and then we can actually start trials in India. তো সেইটার একটা লিঙ্ক আমার কাছে আছে, তাই ইন্ডিয়া will get it quickly if it is approved, but জানবেন only 2% of drugs going into clinical trials are ever successful. তাই জন্য if it is successful, great. If it's not, then we try to make it better. এটাই আমাদের টার্গেট।
Very good question, Aditya.
Very good. Thank you.
Coming from a student, this is a very good question. Very good question. Why you have chosen this drug and how did you choose this particular compound? That is something which is perfect for a student. Congratulations. And
Very well done.
Very well done. So,
Okay.
is there any other questions?
Yeah. Any other questions? If not, তাহলে আমি
mail to him. If there is no questions, then I would request Dr. Zaka Jamal to give the vote of thanks for today's. And I personally would thank Sourav very much for taking some time for us.
No
Thank you
problem
very-
at all. It's been an honor. And thank you for
It's a
being.
privilege for us, and all our teachers are extremely excited, and we find lots of students still waiting for listening to this. Thank you very much. Thank you very much.
Yeah, you're welcome. And thank you for inviting me. That is very, very prestigious for me as well. Thank you.
Thank you very much. And now, Dr. Zaka Jamal, please.
Thank you again, sir, for such a wonderful presentation as well as an enriching one. And we would be looking forward to hearing from you in the future as well. Do join us in the future. That would be an honor. And I would thank our principal, sir, Dr. Amitabh Basu, for his support and continuous guidance. Our HOD, Dr. Rajrupa Ghosh, our IQAC coordinator, Dr. Sudipta Das, our TCS, Dr. Arnab Ganguly, all the students who have participated in this webinar and have made it a successful one. I thank each and every one of them, and thank you once again, sir.
Thank you. Thank you. It's been an honor. Thank you so much.
And Sourav, pass my regards to your mother.
I will do so. I will definitely do so. Thank you so much.
Okay.
All right. Thank you. Hopefully next time আবার দেখা হবে in
হ্যাঁ,
person.
এখানে চলে এসো।
নিশ্চয়ই। Bye. Thank you everyone
Bye,
for
bye.
joining in. Thank you. Bye.
Thank you very much.